Hello, I'm Osman Ceylan. I'm a senior applications engineer at Maury Microwave. Welcome to our virtual exhibition. In this presentation, my colleagues Prakti, Paul, John and I will present understanding your true device performance by including measurement uncertainty. We will explain the main concepts of measurement uncertainty with practical examples in microwave and RF applications. We are going to talk about three technical topics in this presentation. At first, my colleague Paul will introduce the S parameters shortly. In the second part, Prakti will explain classical calibration methods and why we need an enhanced method for uncertainty. After that, John will present several applications using uncertainty information in the third part. You will see how to use uncertainty to improve a measurement setup's accuracy, performance of circuit design, and yield of mass production.
Now to begin our discussion of uncertainty in RF engineering. In this section, I will talk about VNAs and S-parameter uncertainty. Scattering parameters, or S-parameters, describe the electrical properties of a network under linear operating conditions. S-parameters became an industry standard since they were first published in the 1940s. Now they are well-known and frequently used network parameters in the microwave world. Vector network analyzers measure the amplitude and phase of the injected and reflected signals to calculate the S-parameters. A reference impedance is used to define S-parameters reference. 50 ohms is used for most high-frequency applications. S-parameters are used in many applications, from device characterization to mass production. Accurate measurements of S-parameters are essential to improving the performance of the product and increasing the yield ratio. Similar to model measurements, S-parameters also have uncertainties. Therefore, all microwave engineers working in device measurement, modeling, designing, testing, verifying of high-frequency devices, circuits, and systems have to know their S-parameters uncertainties and uncertainty sources to improve the quality of their works and results. Although S-parameter measurements look like a simple measurement method, even when using a brand new VNA, sometimes you may end up with questionable results. For instance, assume that you have to design a power amplifier for a customer with a minimum gain of 12 dB. Your first measurement, which is shown in black, shows the device meeting spec. After a coffee break, you want to show the design to your colleague. You test the amplifier again under the same conditions and measure it. You now notice the device with the same test conditions with a lower gain than your first measurement. The measurement setup, device, and calibration are all the same, but why is it failing now? Let me explain why you see two different results despite the same setup and conditions. In a measurement setup, there are 5 important influences causing problems on a measurement. The figure depicts a regular measurement setup with a VNA, coaxial cables, bias tees, and a DUT. First, a VNA consists of many electrical components and subsystems. Electrical behaviors of these equipment depend on environmental factors such as temperature and humidity. Therefore, their performances drift over time. Second, the operator must move or bend cables, especially during calibration. Physical changes to the cables affect the conductive and isolation materials in the cable, causing phase and amplitude variations. Therefore, the phase response of the cables changes due to mechanical effects. Third, the operator might need to renew connections or land probes several times. These conditions or contacts should be repeatable and properly tightened or landed for accurate calibration and measurement. Fourth, calibration kits are mandatory tools for calibration. Unfortunately, there is no perfect calibration kit providing an excellent correction. For example, coefficient tolerances, physical deformations, and temperature changes cause errors. Fifth, the operator's skills and experience have a direct impact on measurements such as correct installation of equipment, and proper usage of adapters. The most common mistake made when setting up a measurement are using too short or too long a cable, causing mechanical tension in cables and components, not supporting the heavy equipment in the measurement setup properly, and undesired signal coupling between sensitive components, to name a few. After considering these error sources and adding them to the measurement, we can visualize the uncertainty contribution to the S parameter measurements. Depending on the system and amount of errors, uncertainty added to measurement data may vary considerably and cause failures. After measuring our sample device by considering uncertainties of the measurement setup, we observed that some of the estimated measurements fell below the spec and the device failed. In summary, knowing all these uncertainty contributions can allow us to increase the level of confidence in our measurements. This valuable information can be transformed into improved measurement performance and product quality.
Hi, I am Prakti. I'm an applications engineer at Maury Microwave. So let's start by going over the traditional VNA measurement model. In this slide, I will explain how a one-port VNA calibration is done. In this setup, the measurement reference plane is at the right end of the coaxial cable connected to the VNA port. The measurements are done by the receivers of the VNA. There are several components between the VNA receivers and the calibration reference plane, such as couplers, down converters, cables, and adapters. We can model the network between the VNA receivers and the measurement reference plane with a simple two-port network. It is called the error box, and it consists of error coefficients of the network. When we calibrate the system at point 2, the VNA calculates the error coefficients of this two-port network and applies them to the measured raw data to find the corrected values of the measurement reference plane. However, as you have already noticed, the coefficients of this error box are constant values. If there are some parameter changes in the measurement setup after calibration, such as bending of the cable or moving of the connectors, it will introduce systematic errors that will not be accounted for or corrected for, and the measurement data will no longer be correct. Therefore, the calculated error coefficients also have uncertainties. It is possible to estimate residual errors of a calibration with post-calibration measurements. Usually a short terminated airline is used for the measurement. The ripples in the measured data shows the amount of residual errors of the calibration. However, calculated residual errors are sometimes questionable due to the accuracy of the airlines. Besides, they cannot be added to the final measurements. Therefore, it is not possible to consider these residual errors for modeling or design purposes. An enhanced VNA measurement model is a solution to consider random and systematic errors in the measurement. Let's see how. The enhanced VNA measurement model is able to handle additional errors in a calibration operation. The new model uses a cascaded network approach. VNA noise and linearity, classic error box, drift terms, cable stability, connector repeatability, calibration kit errors, and other effects such as probe crosstalk are modeled as sub-networks, and their uncertainty contributions are added to the measurement data. Let me explain each sub-network in the schematic. A VNA consists of many electrical components and circuits. Electrical behavior of these components may vary with time due to temperature and humidity changes. This causes drifting of parameters and changes in the VNA's noise floor. VNA's contributions are mainly modeled by two parameters, trace noise and noise floor. They are measured while the ports of the VNA are terminated with a short. Then a few hundred measurements are performed. Noise floor is the power level of the noise signal generated by the electrical components of the VNA. To calculate the noise floor and linearity, first, maximum values of the real and imaginary parts of S12 and S21 values are considered. To measure S parameters, first, IF bandwidth of the VNA is set. The VNA ports are terminated with a reflect, such as a short, then a few hundred measurements are captured. For trace noise, mean and standard deviation of the normalized magnitude and phase values of S11 and S22 are considered. These values can be taken as the standard uncertainties of magnitude and phase of trace noise. The VNA drift is attributed to the drift in the modeling of the error coefficients. Drift terms are directivity, tracking, and source match. They are calculated as the maximum variations in real and imaginary values of S parameters after 24 hours of measurement with an interval of 15 minutes. To measure the coefficients, a through connection is required after a calibration. Cable stability is modeled by two parameters, cable reflection and cable transmission. To calculate the cable reflection, the cable is terminated with a matched load, and S11 is measured with the cable in a neutral position at first. Then the cable position is changed, and S11 is measured again. After several measurements with different cable positions, the maximum deviation of real and imaginary parts of S11 is considered as cable's reflection uncertainty parameter. Cable transmission is also calculated in the same way, but with a short termination. Maximum deviation of the phase and magnitude of S11 values are considered as uncertainty parameters of cable transmission. Connector repeatability is modeled by one parameter, connector deflection, or CO sub R. CO sub R is estimated after performing a one-port calibration. A short termination is used for the S11 measurement. The S11 of the short is measured several times. Between each measurement, we disconnect and reconnect the connector, and each time we disconnect it, we rotate the termination by a fixed amount before connecting it back again. Standard deviation of the real and imaginary parts of the measured data is used as the uncertainty parameter of connector repeatability. Calibration kits are characterized by simulating 3D models or measurements. But in both cases, there are uncertainties due to manufacturing tolerances and environmental effects. A calibration kit's uncertainty parameters must be estimated and provided by the manufacturer. Characterization of the standards should be traceable to a reference standard. After calculating all uncertainty contributions of the enhanced VNA measurement model's subnetworks, S-parameter uncertainty can be measured. Uncertainty contribution of each component can also be analyzed individually or altogether.
Uncertainty added as parameter measurements can be used in many ways to improve your work's quality. Let's take a look at some of them. In this part of the course, I will present how you can use uncertainty information of S-parameter measurements. The first one is setup evaluation. You can analyze the uncertainty contribution of each component in your measurement setup. The second one is verification and validation of a calibration. Do you still use the same golden device to check your calibration? You'll need to listen to this part carefully. The third one is for design. In this part, I will demonstrate a design example and how you can integrate uncertainty information into your final design and performance evaluation. And the final one is acceptance tests or mass production tests. Every S-parameter measurement setup has several uncertainty sources, as we've mentioned at the beginning of the short course. These include the VNA, cables, connectors, calibration kits, and operator skill. In this example, we measured an RF transistor after configuring the setup with uncertainty. The setup consists of a VNA, bias tees at the input and output of the DUT, 2 cables, and a test fixture. If you look at the uncertainty sources and their weights in the measurement data, you'll immediately notice that the cables and calibration kit have large contributions to the total uncertainty. This is why we recommend phase-stable cables and regular calibrations of your cal kits. It might be time to invest in some phase-stable coaxial cables and to calibrate your cal kits. The image at the bottom left depicts the measurement of an RF amplifier. To measure the amplifier, we extended the ports of the VNA by connecting cables on port 1 and port 2. We then changed the cables to see their performance impact on the measurement of the DUT. The pair of cables used the first time had a very stable performance as compared to the cables used in the second measurement. The image on the right shows the cable's contribution to the uncertainty in the measurement of the amplifier. With the less stable cables, the measurement uncertainty is plus or minus 1 dB between 3 to 4 GHz, while the stable set of cables is less than 0.1 dB. If we look at the uncertainty budget, we can see that 99% contribution to uncertainty is coming from the cables, which tells us that cables are a major source of uncertainty in the measurement. Many engineers keep a known reference device or a calibration standard called their golden device to validate the most recent calibration of the setup. In most cases, the user compares the reference characterization with the actual measurement and estimates how close the two are. But how can you be sure that your trusted measurement is also good? After all, you are the one defining the references and acceptance conditions. For example, here we see two measurement data up to 18 GHz. Is this an acceptable calibration? Is it good in a particular frequency range? We can see that there are some small differences around 4, 10, and 12 GHz and a clear separation after 15 GHz. How can we decide to continue? Most of the current verification devices are not characterized with uncertainties, and so it is difficult for the user to specify an adequate requirement for the validation. A better decision can be made with uncertainty included in the measurements. There are two conditions to decide if a calibration was successful. The first is if the setup has low uncertainty, and secondly, if both of the measurements, the reference and the recent measurement, have a similar uncertainty trend. Then this can be considered an excellent calibration. In this example, there is an obvious separation between the uncertainty trends above 15 GHz. Therefore, we can consider this a bad calibration. In this slide, we have a power amplifier design example to explain how uncertainty information can also be used for design. In this design, we have a gas FET transistor. Its S parameters are measured with uncertainty. Then we design a narrowband amplifier at 2.4 GHz based on S parameters. After completing the design, S parameters of the input and output matching networks are imported into the Insight software. Then, the input matching network, transistor S parameters including uncertainty information, and output matching network are cascaded. The software calculates the final circuit's uncertainty. If we look at the uncertainty added results, the S11 uncertainty of the transistor is plus or minus 0.07 dB. It becomes plus or minus 6.4 dB in the final design. Similarly, the uncertainty of the S21 parameter of the transistor is plus or minus 0.07 dB. The final amplifier design has plus or minus 0.5 dB gain variation. Assume that there is no tolerance on the components and you fabricate this amplifier. If the final amplifier's design requirement is a minimum of minus 20 dB of S11, some of the amplifiers can fail the acceptance test due to the uncertainty of the transistor's S11. This is a great example of how uncertainty information can provide valuable feedback. You can check your design, try to reduce your measurement setup's uncertainty, etc. There are many steps in a product fabrication that reduce yield ratio, such as wafer level fabrication issues, packaging, bonding wire tolerances, etc. These are physical effects and a test engineer cannot really change them. In general, final yield is a function of normal distribution. In this slide, you can see the yield differences between two measurement setups. A setup having smaller uncertainty has increased yield. You can revise your acceptance criteria and thus save millions of dollars in mass production. How do you present your measurement data to your customer? If we look at data sheets, we see three values for each parameter: minimum, typical, and maximum values. The presented data do not show the weights of the contributions causing the variation. Presenting additional information with uncertainty will provide more confidence on data sheets. Uncertainty information can be included with statistical analysis to verify if devices produced in mass quantities meet the acceptance criteria.
Thanks for your attention. If you have questions, please feel free to send an email to insight.support@maurymw.com.